Morning, students. Last lesson of digital communication, we have observed, you can see in your screen, we measured the bandwidth requirement of time division multiplex signal, and our conclusion was that same bandwidth, the channel needs the same bandwidth as if it was an analog communication and frequency multiplexing was done. Next, we go to the next topic, which is PDM PAM bandwidth requirement we have done already. We now go to the next topic of quantization. What is quantization really? Let's go into detail. We have obtained sampled pulses, right? Now, sampled pulses has to be converted into binary digits, 1001, something like this. Now, what is this process? Yeah, before just converting into a binary digit by a to D converter, there is another step which is called quantization. Basic of source transmission is to convert the original analog signal to digital. That's fine. You see in your picture, you can see the sampled signals, a train of samples. Then we have to convert them, each sample, we have to convert them into a digital number or a binary number, right? Now, you could just put this sample input to a AD converter, A to D converter, it will give the binary output. But before that, but if you do that, there is a problem. What is the problem? Amplitude values of these samples could be converted to binary numbers and conveyed to the receiver in the form of a binary waveform. That's what we said. For example, if the sample value is 5 volt, an waveform representing 101 could be transmitted because binary equivalent of 5 is 101. So this is a 5 volt sample, you transmit 101. And when the receiver receives 101, receiver will easily understand it is 5 volt. But what if the sample value is 5.0037 volt? Then you are in a problem. If you want to convert 5.0037 into binary, you need a long binary bits and number of bits, and also this number of bits will vary from sample to sample, because if one sample is 5 volt, you need 101. But if next sample is 5.0037, you need a long binary data. So what is happening? The receiver will be in confusion that where a data starts and where a data ends. Because one data is 3-bit, another data is maybe 30-bit. Receiver will be in a serious confusion. To understand where the symbol starts. Circumvent this problem. The problem can be eliminated by quantization. What is quantization? Now, the entire signal is divided into some defined number of steps. For example, 8 steps. Say your signal amplitude may be plus minus 10 volt, right? So this total amplitude of 20 volt, you divide into 8 steps so that each step is 2.5 volt. Now you can divide it in 8 steps, you can divide it in any number of steps, right? If you divide it in 8 steps, then each step assigned a value is assigned a value, say from 0 to 7. These are the 8 steps, and each step is assigned a value 0 to 7. Normally, in binary communication, it always starts from 0, not from 1. 0 to 7 steps. So when, say, the first sample, when the first sample is here, it is in number 4 step. Second sample is number 2 step. Third sample is in step number 5, right? So you can find out, you can always determine, or some circuit can always determine from the value of the signal, it can determine in which step range it is, right? So long the sample value is anywhere within a step, its value is assumed to be that step number. For example, as long as you see the cursor of this, as long as the signal is within this band, considered step number 4. As long as it is within this band, it is considered step number 6. So when it is in step number, by 3-bit conversion, you send the data 1 0, you send the data 1 0 0, right? When it is step number 6, you send the data 1 1 0. When it is step number 7, that is 8th step, you send the data 1 1 1. So for 8 steps, all the 8 steps, you can send the data by a 3-bit binary number. Values of these 6 samples that you see here are step number 4, first one, second one is 2, third one is 5, then is 6, then is step number 4, then it is in step number 1. All these values can be from 0 to 7, can be represented by a 3-bit binary number. So now the receiver will not have any confusion. He will always get a 3-bit number, and when he receives the long transmission, every fourth bit will know that it is the start of the next symbol. So that problem of confusion goes away. Obviously, the number of steps is always 2 to the power n. But now, since you are using binary number, and if you have 3-bit, then there are 2 to the power 3, that means 8 possible binary numbers. If you choose 4-bit, then 2 to the power 4, that means 16 possible binary numbers. So the number of steps of quantization will be always an index of 2, some power of 2, either 2, 4, 8, 16, and 32, then 64, then 128, like this. There will be no quantization where the number of steps is 13 or 19. It will be always 2 to the power n. That is clear from this picture. 6 quantized sampled values, 4, 2, 5, 6, 4, 1, the receiver will reconstruct these values. Because this is for 4, receiver will get 0, receiver will get 1 0 0. For 2, receiver will get 0 1 0. For like corresponding binary number, binary digits, the receiver will get. And the receiver will, by a D to A conversion, that means digital to analog conversion chip or circuit, it will automatically clear the values, recreate the values. But the problem is, it is first sample, it is in step number 4. But step number 4 is a wide step. If the whole range is plus minus 10 volt, then step number 4 may be a range of 2 volt to 3 volt, maybe, right? So, actual signal can be 2.3 volt, can be 2.7 volt, but we are always considering it to be 4 and sending 1 0 0. So, there is an error. Obviously, If you make the step very small, then error will be small. If you make the step large, then error will be large. Because if in a large band, the possible values are much larger possible values, right? But we are taking one average value of it. And this error is called quantization error because the error has cropped up because of quantization, right? Sometimes they ask you in your exam, what is quantization error? Quantization error is due to quantization because after quantization, we take a mean value of a particular step. And if the signal is within that step, anywhere within that step, we take a single value. So obviously there is a possible error. Now we are trying to find out this quantization error is also called quantization noise because it is as if some noise has gone into the system and it is altering the sample values. So you can call it quantization error or quantization noise. It means the same thing. Now we shall try to find out how much is the measure of quantization error. Look at this picture. Say exact value of the sample is m, this value, right? Quantized value is mq. So this is the step. This is the step. And just at the middle of it, the value is mq, say, right? So, but actual signal is m, but I have considered it at mq. So what is the error? Error is m minus mq. This is the error, right? Now, what is the mean square error? Mean square error is all such errors square and then mean or means. That means m minus mq square bar, right? Mean. Mq, this mq, that means the quantized value, is of course the mean of any step. Mean means just in between, at the middle of mean of any step. Hence, the mean square to the variance of the sample value within the step. I think this mathematics you have already done in your mathematics class or some other class. Minus mq square bar. I mean, this signal continues and there are repeatedly many values of m, in various samples, and there is one value of mq, and mq is the mean. It is in the middle of the step, and m minus mq whole square bar is mathematically equal to the variance of the signal within that step. In practice, the step size is very small. Hence, probability of the exact sample value within a step can be assumed to be uniform. Here we are going into the mathematics. If the probability, that means the signal m, can be anywhere within this range S, and if this range S is small, we can consider that the probability of M being above MQ, below MQ, or anywhere above or below MQ is uniform. That is uniform probability. What I mean, the probability of signal value M to be, say, 1 millivolt above MQ or 1 millivolt below MQ is same. It's called uniform probability. And you can always apply uniform probability if the step size is very small. Assuming the step size to be S, the variance and hence the mean square error of the step is s square by 12. This is a standard formula. Standard formula in mathematics or statistics, variance is given by s square by 12, where s is the range square by 12, right? Since all step sizes are same, so overall mean square value is also a square by 12. So if square value or the variance mean square error is by 12 here, it is also a square by 12 in some other step or some other step. There are maybe same 7 or 8 steps. In each step, the value is same, a square by 12. So overall average over the range of the signal amplitude plus minus V is also a square by 12. It is clear that this error is a square by 12. That means step size square by 12. So obviously, the smaller is the S, the smaller is the error. Error is smaller when step sizes are smaller for larger number of steps or levels. That means if you make 3-bit conversion, there will be 8 steps, there will be more error. If you make 4-bit conversion, then there will be 16 steps, error will be less. If you 8-bit conversion, error will be further less. So what do you find? This error produced by quantization depends upon the number of steps, how many steps you are taking. For costlier equipment, the number of steps will be more. For cheap equipments, number of steps will be less. And when you listen to the voice or when you listen to the song, you will find more disturbance or irritation. Next, we derive a mathematical equation. Assume the signal is zero mean. What is meant by zero mean signal? Signal, say audio signal, is practically a random signal. But if you take all such random samples for a duration of say 5 minutes or 10 minutes and take their mean, it will be zero. That is called zero mean signal. And it is true for all natural and practical signals. The signals are zero mean signals. Assume that a signal is zero mean and its range is minus V volt to plus V volt. And the probability of the signal to be within this range is uniform. That means the probability of the signal to be anywhere within plus minus V is same. And this is true for practical signals. It is like this is a picture of a signal. Range is plus V, minus V to plus V. This is a signal. And we consider its probability to be anywhere within this range is same. Then variance or power of the signal, what is the total range? Plus V to minus V, that is 2V. So it will be 2V square by 12. That is standard formula of variance. 2V square by 12 is 4V square by 12, that means V square by 3. I think you all know that this variance is also the statistical signal power. This, I do not want to go into that mathematics now. This variance is a variance of a zero mean signal is also its signal power. So signal power is V square by 3, right? If it is not a sinusoidal signal, if it is a sinusoidal signal, you can calculate by your standard equation and find out the power. Power is equal to S square by 2, something like that. S square by root 2, I think. But anyway, in statistical signal, it is V square by 3. Now let us say there are 2 to the power n quantization levels. That means if you consider n equal to 3, then 2 to the power 3, that means 8 quantization levels. And n, automatically, n signifies the number of bits of transmission for each sample. Say there are 2 to the power n quantization levels, so that Each symbol can be coded into capital N number of bits. What will be the step size? Plus b minus b, that means 2b divided by 2 to the power n. So s equal to 2 to the power 2b by 2 to the power n. Fine. Then what is the quantization? What is the quantization noise we found just in the last page? Quantization noise in the last page we found s square by 12. So s is 2b by 2n whole square by 12. This is equal to 4 square 4v square divided by 12 multiplied by 2 to the power n, 2 to the power 2n, because it was 2 to the power n whole square, 2 to the power 2n. This is equal to v square by 3 in quantization noise, right? And this is the signal power. This is the quantization noise power. This is the signal power. And in communication technology, are really not much bothered by the signal power itself or noise power itself. We are always bothered about the ratio of them. Signal to noise ratio, which is called SNR, signal to noise power ratio. So, what is the signal power to quantization noise ratio? Signal power was V square by 3, V square by 3. Noise power is V square by 3 into 2 to the power 2n, V square by 3 into 2 to the power 2n. This is V square and V square will get cancelled, 3 and 3 will get cancelled, so it is equal to 2 to the power 2n. So, signal to noise power ratio is 2 to the power 2n. Of course, from here we find if n is large, ratio is large, that means signal and less noise. This equation you must remember. Signal to noise power ratio is 2 to the power 2n. But we normally, the power, intensity, etc. in communication engineering, we represent in terms of decibel. This is the ratio. Decibel is 10 log 10 the ratio. So 10 log base 10 to the power 2n, and this will be 10 multiplied by 2n, that is 20n multiplied by log 2 base 10. Log 2 base 10 is 3. So it is a 6n dB, 6n decibel. This figure you must remember very, very well. Noise ratio is 6n decibel. That means n by the value of n by 1, then the ratio increases by 6 dB. That means signal to noise ratio improves by 6 dB for 1 extra bit in binary conversion. That means if you are doing 3-bit conversion, and if you find the signal to ratio, noise ratio is 10 dB, and if you now try 4-bit conversion, signal to noise ratio will be 10 plus 6, 16 dB. That means signal will be much higher than the noise. Is quantization noise? What is quantization noise and what is the measure of quantization noise? Then non-uniform quantization. Suppose a quantizer has been designed for a signal range minus V to plus V. Now, but on a certain occasion, the actual signal is within V by 2 and V by 2. That means it is like this. You have designed an instrument, we have designed an electronics for a signal range plus minus V. But you find that for a few days or for a certain occasion, the signal is very small. Signal is within plus minus V upon 2. Right? within plus minus signal is very small, plus minus V upon 2, right? Then this is I'll give an example. Suppose if you have designed an audio system for shouting at the mic, but a singer comes whose voice is very soft, so his signal strength is much smaller. In that case, your actual signal handling will not be as per design. Then what do you do? We have a technique in that. So we have taken an example. Suppose the signal range is V by 2 minus V by 2 to plus V by 2. That means total range is V. The total range is V, total step is V, then total signal power is V square by 12. We have seen just a few minutes back, the signal power is the peak-to-peak amplitude square by 12, right? Now, what will be the signal to noise ratio? Signal power is V square by 12, but noise was found capital V square by 3 into 2 to the power 2n. We have found it earlier. Because noise will be more because you have designed the system for plus minus V range of the signal. And accordingly, you have designed the quantization electronics. So your quantization noise will be as per your design, which is V square by 3 into 2 to the power 2n. So signal to noise ratio becomes 2 to the power 2n by 4. What was the signal to noise ratio earlier? It was 2 to the power 2n. Now it is divided by 4. That means signal to noise ratio has deteriorated to about 25% of the design value. This means signal to noise ratio worsens to 1/4 of the design value. This is a problem. In order to avoid such problems, what do? We have designed a system for a range of signal plus minus V volt. And we always want the signal to be within this range, not very small. So we design a circuit like this is a nonlinear amplifier where this is the input, this is the output. You see, when the input is small, then slope of the curve is larger. That means amplification is large. And when the input is higher, then slope of the curve is smaller. That means amplification is smaller. This is a nonlinear amplifier. Now we say, in order to avoid this problem, that noise ratio, what is the problem? Signal to noise ratio have worsened in case of loss. Avoid this problem, what do? The signal can be initially passed through a nonlinear amplifier at low input and low at high input. This process is called compressing the signal, right? That in order to revive the original signal at the receiver end, you need an amplifier having just the reverse characteristics, where its gain will be small at smaller amplitude and of the signal, and its gain will be high at the larger. It has to be just reversed to come back to the original voice quality. Obviously, a reverse process known as expanding. This was compressing, this was expanding, is applied at the receiver, where low signal is amplified less and high signal is amplified more. Now, if you join these two words, compressing and expanding, these two things together is called compending in communication engineering. So this process is called compending. This process, compending process, you can use if you find that the signal range, actual signal range, is varies much. If you have an audio amplifier and a mic, and all your friends are singing, and everybody is shouting at the mic, there is no problem because you have designed the system for shouting. But if you find that one of your friend is singing at a very low voice, then there will be the noise will be much higher, and that low voice song will be very noisy. In that case, you use this compending method, right? Now, this card, this card really, now since this signal will be low or high, this is all random. You do not know which of your friend will sing at a low voice and which of your friend will shout at the mic. So really, there is no mathematical formula for creating that nonlinear curve. But out of various practical statistics that how people behave at the mic or how people shout or talk at the mic, some two worldwide standards have been created. One law is A law, another is mu law. Mu law is normally followed by US, Canada, and Japan, and A law is followed by rest of the world. Here, Y is the output of the expander, right? Now, output of the compressor. X is the input, right? So the function Y as a function of X is given by this equation. It is pretty difficult to remember this equation, but if you can memorize, because your exam they may ask what is A law, mu law. If you can remember, you can put this. You can if you memorize, you can put this equation. Y is equal to plus minus log of 1 plus mu mod x divided by log of 1 plus mu. Now, what is mu? Mu is a certain value. Normally, in US, Canada, and Japan, mu is 255. And of the design is plus minus V volt. And what is X? X is actually I divided by V. That means signal to range ratio. Signal may be half of the range, signal may be one-fourth of the range. And Y is equal to output voltage divided by range, right? And this is the equation used for this nonlinear curve. A law is used by rest of the world, including India, where this is the equation. Here also, x, y, that means output y as a function of input x is given by this equation. And here also, x is equal to the ratio of input voltage by the signal range, design range. Y is equal to output voltage divided by design range. And the value of A normally used by rest of the world is 87.6. It has been found that if you use this formula, then it works almost okay everywhere. But because you cannot design your audio amplifier for a particular singer or a particular speech, right? So this is A law, mu law. So what we have learned today, we have learned what is quantization and what is compounding, and there are two methods of compounding, A law, mu law. Now we are, after quantization, we are having quantized sample values. That means you may have an input signal and they have been quantized into 8 particular values. Right? Let's say 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, 6 volt, 7 volt, 8 volt. 8 quantized values. After quantization, you do not have any value 3.404. You do not have such. You have 1, 2, 3, the integer values. And if you have 8 values from 0 to 7, you use a 3-bit A to D converter, analog to digital converter. You have a 3-bit conversion. And each symbol will be transmitted by a 3 binary bit. Receiver also will know what are the 3 binary bits, and it will receiver will use a D to A converter, and receiver will find out there's all those sample values. It is a picture here. After sampling and quantization, what remains is only converting the analog value of quantized samples to binary signal numbers. And in its very simplest form, it can be simply done by a to D converter. There are standard chips available, A to D converter. This is a picture showing you, let's say this first sample value, it is more than 1 but less than 1.5. So we have measured it to 1.3 volt, right? And what is this quantized value? Is the value between 1 and 2, this line. This is line 1, this is line 2. Value between 1 and 2 is 1.5. This is the quantized value, 1.5, right? Similarly, second sample is here, which is minus 1.1. If it is minus 1.1, then it is in this range. It is in this range, and it is the quantized value is minus 1.5. So there are these 6 different values, and we have allotted them code 0 to 7. So first quantized value come to 5. This one comes to 5. Step 5. This one comes to step 2. So if it is 5, you send 101. If it is 2, you send 010. So this way you keep on sending these bits. This is pulse code modulation. We revise once again. First we have the signal, then ending if necessary. We use compounding. Then we use sampling. After sampling, we do quantization. After quantization, we find these quantization steps of the signal, on which step it is 2, 4, 7, 5, 2, 5. And these integer values we put to a to D converter. A to D converter gives me an output signal. This signal, binary signal, is transmitted. This is called pulse code modulation, right? This is what is called pulse code modulation. Here there is just a schematic. This is our signal. Here there is an anti-aliasing filter. Now, I have not talked to you about this filter so far. The important equipment. Anti-aliasing filter is, we have discussed that we have said repeatedly, let us consider that the signal is band limited to FM. That means maximum frequency content of the signal is FM, which may be 10 kilohertz, let's say. Now, who knows? One of your friend who comes onto the stage to sing onto the mic may have FM 12 kilohertz, and he will corrupt the entire audio system. So, if my design is 10 kilohertz, then at the very beginning, I use a filter of 10 kilohertz. That means even if somebody tries singing at more than 10 kilohertz, very high pitch, then that is cut off, filtered out, so that it does not corrupt the entire system design. That is anti-aliasing filter. Then we use compressor with A law, mu law. Then you use sampler, or we do the sampling. Then you use quantization. Then you use A to D conversion, which we call encoder, and then it goes to the channel. So this is a scheme of pulse code modulation. Fine. We shall go to uh, more and more advanced form of pulse code modulation. The next day our lesson will be differential pulse code modulation, right? This one, the basic pulse code modulation system. We have learned what is pulse code modulation. Next day, we shall go to other advanced form of pulse code modulation. Okay? Bye then.